Chapter 8, Introduction to Hypothesis Testing, Part 4. In the previous video, we ended discussing the four-step process when we engage in a hypothesis test. I'm going to use those four steps to model the example in the text pertaining to the electric stimulation in relation to its effects on mathematical skills. So step 1 states that we must first identify the research and null hypothesis and select an alpha level. So for this example, we can state our null hypothesis as such. The electric stimulation will not, again, the null says nothing's going to happen, no change, will not have an effect on math skills. And in this particular example, we were told that the average standardized test score was equal to 80. So that was a given. And we were also told that the standard deviation for that population was, or that test, the standardized test was equal to 20. So those are givens. All right, and therefore the null would state that the mu treated would equal 80. That given the selection of a sample of individuals who received this electric brain stimulation, that we would anticipate, given the null, that their standardized test score average after treatment would be equal to the untreated population, which was also equal to 80. Again, we would state and understand that there would be no change. The research hypothesis, on the other hand, would say that the electric stimulation does have an effect on math skills. And the proper mathematical notation, again, we're hypothesizing about this treated population, and we would anticipate that their average would not equal 80, because again, the research is saying something's going to happen, there will be a change, and we're expecting that change to be significant, but we're going to put this value that we obtained from the sample to the test to determine if it is statistically significantly different from 80. But again, make sure that you understand the ability, you have developed the ability to state the research and null hypothesis. Again, what may help you is first identify the independent variable. What is it that we're manipulating? It is administration of this electric stimulation. That's the independent variable. And what do we anticipate it will have an effect on? Math skills. So that the math skills is the dependent variable. Sometimes identifying the independent dependent variable helps you verbalize what those two hypotheses would look like. The independent variable will not have an effect on the dependent variable. Again, you can just leave those as blanks and insert what the independent and dependent variables are so that the articulation of the research and null hypothesis is more structured and easier for you to develop. Some students have difficulty doing this, so this is just one strategy that if you identify the basic structure, the independent variable will not have an effect on the dependent variable for the null hypothesis. It's just a matter of inserting what the independent variable is and then also identifying what the dependent variable is. All right, so it also indicates in step 1, which is sometimes put into step 2, but here it's specified within step 1, we identify an alpha. So let's say that as researchers, we identified that we're going to use 0.05, which is the same as saying we're looking for something that has less than a 5% chance of occurring. Locating the critical region means that we're going to identify what that key z-score is when we've identified alpha to equal 5%. So if that's the case, we're saying 95% is in the center, or 0.095 in the center, and we have 5% split across two tails, which means we have 0.025 here, and similarly 0.025 on the other side. Again, that's 2.5% and 2.5% for a total of 5%. And we know that when we enter the unit normal table and we find this value of 0.025 in the tail, you'll find a z-score of negative 1.96 and its corresponding positive value of 1.96. So we've identified the critical region. In other words, any z-value that falls in this region or in this region, we get to reject the null hypothesis. Next, it says collect the data and compute our t-statistic. Now, normally in the real world, we would collect the data, but for this example, we've been given a sample mean value, which was equal to 89. So M is equal to 89. I'm going to use a different slide to then compute our t-statistic using the sample statistic of M is equal to 89. The sample mean is equal to 89. So here I've identified the given values. The population mean for this standardized math exam was equal to 80. The average score is equal to 80. And the distribution is normal. The standard deviation for that distribution was equal to 20. And we selected 25 individuals to receive treatment, and after treatment, after they received this electric brain stimulation, they were given this standardized math test, and their average score was equal to 89. So our third step indicates that we must compute the test statistic, which essentially means convert that sample mean to a z-score. So our equation is z is equal to m minus mu divided by standard error. If we replace variables, we know our sample statistic is equal to 89, our population mu is equal to 80, and we recognize what we're missing is the standard error of the mean. So the standard error of the mean is equal to standard deviation over the square root of n. If we replace variables, the standard error of the mean is equal to 20 over the square root of 25. Let me just clean that up just a tad. So 25. And we have 20 over 5, and that gives us 4. So over here we can include that in our equation now. What we're saying is that in a distribution of sample means, the average difference between a sample mean and the population mean is equal to 4 points. So now if we want to calculate our z-score, or our test statistic as we refer to it, we would take 89 minus 80. So z is equal to 9 over 4, and that is equal to 2.25. So what we're saying is the sample mean of 89 is 2.25 standard error units from the population mean equal to 80. And that's how we complete step 3, which again indicates that we compute our test statistic. Essentially, what that means is simply taking our sample mean and converting it into a z-score so we can determine its location and then also understand the probability of that value occurring if the null is true. The null states that nothing will happen given treatment. We will not see a difference between the means. So let's just have a brief conversation about, do we see a difference between the mean? Is 89 different from 80? Numerically speaking, we would conclude that 89 is not equal to 80. And I'm sure you would agree with that. But what we need to determine is if the difference between 80 and 89 is statistically significant. In other words, is it large enough for us to say that, yes, these values are different enough that the ability or the probability of obtaining a sample mean average equal to 89 is very unlikely if the null is true. In other words, if we randomly selected 25 individuals from the untreated population, it would be very unlikely that those 25 individuals without treatment would generate a sample mean equal to 89. Now, if that value of 89 is really closely centered around the mu, then we would conclude that obtaining a sample mean equal to 89 by randomly selecting 25 individuals from the untreated population, if that z-score is close to 0, then we would conclude that the value of 89 is statistically no different than the value of 80. And the reason is that the difference, it would be attributed to sampling error. It was just by chance. So again, the proximity of that z-score to the center will determine if we reject or fail to reject the null. So here we have a notation where in the center where it says fail to reject the null in the white, this notation indicates that the probability is greater than alpha. Again, alpha was set at 0.05. So values that fall in this region, again in the center we have a z-score equal to 0. So the closer your z-score is to 0, the higher the probability of that value occurring if the null is true. Therefore, we would see that the probability is greater than alpha, greater than 0.05. In the tails, we see the statement probability less than alpha, right? Meaning that those values have less than a 5% chance of occurring if the null is true. So, given the value of 2.25 and what we had identified as our critical region z-scores, we had determined that our values were set at 1.96 and positive 1.96. So our job now is to draw conclusions based on the probability of this z-value. Does it fall in the common region centered around a z-score of 0, or is it falling in the blue highlighted areas which have lower probability and indicate that we do see treatment effect, or at least we have support that something is happening? So let's look at this value and place it accordingly. So it's a positive value, so we're going to be focusing on the right side of the distribution. And because it's greater than 1.96, let's just place it here, 2.25. It falls in the blue region, and as a result, we get to reject the null. Again, the null says that there's no difference between 89 and 80. So initially, we're thinking, what the null is stating, that 89 is equal to 80. Again, numerically speaking, we would say that that's not true, but statistically speaking, the null says they're no different from each other. But now we've concluded that this value is far from 0. It's out in the tails for far enough where we can conclude that the probability of that value occurring is very unlikely. So now we, again, understand numerically speaking and statistically speaking, these values are not equal to one another. So the last step of our hypothesis test simply states that we have to make a decision. So let's go back to how that fourth step is demonstrated and what we need to do to draw proper conclusions. So here it says step 4, make a probability-based decision about the null. We reject the null if the test statistic, our z-score, is unlikely when the null is true. And this is referred to as statistically significant. So given that diagram, we've concluded that we get to reject the null hypothesis. It is very unlikely that we would obtain a sample mean of 89 based on 25 randomly selected individuals from the untreated population. That sample mean has less than a 5% chance of occurring in the untreated population. I'm trying to stress it, and I fumbled there. It's the untreated population that we're looking at. So that sample mean of 89 is very unlikely to occur when we select 25 individuals at random. It's very unlikely that they're going to generate a sample mean equal to 89. And that's what we were seeing in that particular graph. So let's go back to that. So again, the probability is less than alpha, and therefore we get to, again, reject the null. We get to conclude that 89 is numerically different from 80, but also statistically speaking, it's different from 80 in the sense that it has a very low probability of occurring if the null were true. So let's discuss how we would actually write this up in a research report, in fact, APA format. You'll encounter these kinds of conclusions in a research study, and now that you see all the steps that went into the test, you'll be able to better understand the concluding statement that is provided. There is special language and notation required when you publish the reports of a hypothesis test. Again, a result is significant or statistically significant if it is very unlikely to occur when the null hypothesis is true. In this particular example, we did see that the z-score or test statistic fell in the tail, and therefore it was deemed as very unlikely to occur if the null were true. In this case, the null was indicating that the electric brain stimulation would not have an effect on the math test scores. So our conclusion was to reject the null. When we cite this in a report, we need to follow these three bullet points, which are we report what we found in terms of whether it was significant or not. For in this case, we could write that the results indicate that the electric brain stimulation had a significant, and we can say significant because we've deemed it to be statistically significant, had a significant effect on math skills. In particular, in this case, it was the math test scores. So that's how we operationalize. The skills were determined by the change in test scores. Next, it says report the value of the z statistic. So then we would include a comma here, and then our z statistic was equal to 2.25. And then the third component is report the probability statement, the p-value for your test statistic. And we determined that the probability of obtaining that z-score, the probability of this z-score occurring if the null were true, is less than our set alpha at 0.05. So your written conclusion must include these three components. Again, determine if it was significant, report and include the test statistic, your z-value, and then your probability statement will be the last factor that you include. In this case, we indicated, or we found that our t-value, right, was over here, 2.25 in the tail. And that was equivalent to saying that it had less than a 5% chance of occurring. Let's look a really quick look up a z-score of 2.25 in a unit normal table and look at the tail proportion, which indicates the probability of that value occurring. So here's our unit normal table, our z-value of 2.25, and in the tail we have 0.0122, or a percentage of 1.22%. So again, that's less than 5%. Technically, it's 2.5% in each tail, but nonetheless, we're saying that this value, this z-score, has less than a 5% chance of occurring. That's what that notation refers to. So just a little hint, when you do see p less than alpha, and again, we had identified this initially, at the beginning of our hypothesis test. If you see p less than the alpha, then that means we're going to reject the null. And if we see p is greater than alpha, that means that we fail to reject. So I highly recommend that you put those in, you put that in your notes. That again, if you see the concluding statement indicating that the probability of your z or test statistic is less than alpha, then that is the same as saying we reject the null hypothesis, because that's indicating that this z value or test statistic is falling in the tail of that distribution of sample means. Assumptions for hypothesis tests with z-scores. The mathematics used for a hypothesis test are based on a set of assumptions. When these assumptions are satisfied, you as a researcher can be confident that the test produces a justified conclusion. In practice, researchers are not overly concerned with the assumptions underlying hypothesis tests, because the tests usually work well even when assumptions are violated. However, you should be aware of the fundamental conditions that are associated with each type of statistic test to ensure that the test is being used, that the test is being used appropriately. The assumptions for a z-test are as follows. First, random sampling. We understood and learned that random sampling refers to the process of sampling with replacement. And essentially, it is assumed that the participants used in the study were selected randomly. And again, we wish to generalize our findings to the sample, from the sample to the population. Therefore, the sample must be representative of the population for which it has been drawn. And obviously, engaging in sampling with replacement ensures that everyone has an equal chance of being selected. And if there are multiple selections, that when we replace those individuals back into the pool, they have the ability to be selected again. And by engaging in random sampling, we ensure that that sample is going to be representative of the population for which we're going to draw conclusions. Independent observations. Which again helps to ensure that the sample is representative of the population and that the results can be rightfully generalized to the population. The third assumption is that the value of the standard deviation of the population is not changed by the treatment. And this assumption stems from a general assumption that we've discussed in the past, and that is that the effect of treatment is to add a constant amount or to subtract a constant amount from every score in the population. Again, we learned that we had a rule, a scaling rule, that said the new mu would equal the original plus or minus a constant. So we know that if there's a treatment effect, we're adding a certain amount of points to each score, which means that the whole distribution is going to shift either upward if we're adding or shift downward if we're subtracting. And we also learned that it had an effect when we add or subtract a constant, that the new standard deviation, which is reflective of variability, was equal to the original. In other words, the addition or subtraction of a constant to every score moves the distribution up or down, but doesn't change the shape. Again, the shape is an illustration of variability, and the statistic we use to express variability is the standard deviation. So the assumption lends itself to accepting that we're working with a normal distribution and the shape, right, doesn't change. In other words, if the original population was normal and this center score was 50, and we had a treatment administered, and now the whole distribution moved upward and all of the scores increased and the new mean was equal to 100, again, the shape of the distribution just is unaffected. We're just talking about a move in the mean values, or a difference in the mean based on treatment. So again, this assumption lends itself to the importance of the shape of the distribution, the normal shape that is required for us to implement probability in the unit normal table. However, it's important to state that this assumption is theoretical, and in actual experiments, a treatment generally does not show a perfect and consistent additive effect. In other words, if we administer treatment to a group of individuals, we assume that everyone's score will change based on the treatment, and the theoretical ideal is that they will consistently change. In other words, each person will increase by 5 points. But in reality, we understand that it may be there may be some fluctuation in that. Nonetheless, these assumptions help us engage in this type of hypothetical testing procedure, and we recognize this, but this engaging in these, apologize for that brief disruption. So again, I was saying that the assumption, this third assumption, pertains to the idea that the distribution is just moving upward or downward, but no change is resulted in the variability. The variability remains consistent. And the last assumption is that we're dealing with normal distributions, so normally distributed sampling distributions. And we'll recall that in order to obtain a normal distribution or create a normal distribution of sampling means, we had to meet one of two criteria. And the first was that the original distribution, and I should say population distribution, is normal, or n is greater than 30. So as long as we meet one of these two, we will produce a distribution of sample means that is normal, and consequently can utilize the concept of probability in the unit normal table to determine if a sample mean is unlikely or likely, so that we can draw our conclusions regarding the null hypothesis. In other words, do we get to reject the null, or we fail to reject the null? Factors that influence the outcome of a hypothesis test. Again, we're hoping to reject the null hypothesis when engaging in hypothesis tests. To do so, we must produce a z-statistic or a test statistic that's out in the tails, meaning a large z-value, whether it's negative or positive. So given the equation of how we generate a z-value, z is equal to m minus mu over the standard error. Let's discuss how changing any of these variables will have an impact on our z-value, right? Because again, we want z-values out in the tail, right? Out in the tail. And by producing a z-score out in the tail, it enables us to reject the null hypothesis. Let's just take, for instance, negative 1.96 and positive 1.96. So a z-score of 1.97, negative 2.0, all of those would fall in the critical region. So again, let's say it's 2.05 negative or 2.05 positive. Again, those are values that would enable us to reject the null. Notice the numeric value is increasing. On the negative side, that has different implications, but we're talking about the numeric value. As that value increases, it goes further out into the tail. So that's what we hope for. So let's see how the change in these different variables affect our z statistics. So in the first case, it says the size difference between the sample mean and the original population mean. Larger discrepancies yield larger z-scores. Well, let's put that to the test. Let's say the example of the electric stimulation. One sample mean that was discussed, and we walked through the steps, was 89. So again, z is equal to 89 minus the population mean of 80 divided by the standard error, which was equal to 4. And we had produced a z-score of 2.25. Now let's say instead of m equal to 89, let's say it was less than that. Let's say m was equal to 84. So 84 minus 80 divided by 4 gives us 1. So again, larger discrepancies between m and mu, again, we refer to that as the mean difference. So the larger that mean difference, the larger the z-score. Is that true in this example that we just showed? So when m was equal to 84, we generated a z-score of 1. Notice 1 would fall somewhere close to the 0, right, and not enable us to reject the null. Whereas when 84 became 89, increased, right, larger discrepancies between the sample mean and the population mean, larger mean difference, produced a larger z-score, which now falls into the tail. So again, recognizing how these variables change, what they mean for the z-score, helps us better conceptualize our conclusion. And that should make sense, right? Because what we're saying is that the treatment effect will change the mean. We expect the treated population mean to be different than the untreated. If we don't expect that, there's no reason to engage in a hypothesis test. So large discrepancies between the sample mean and the population mean will produce larger z-scores. I'm going to erase all of this so I can go through the next bullet points with you. And the next one, variability of the scores. So more variability lends itself to larger standard error and generates a smaller z-score. And again, this is all determined mathematically. So again, z is equal to m minus mu divided by standard error. And we know that standard error is equal to standard deviation over the square root of n. So let's just play with some numbers. So again, we're saying more variability. Again, we're talking about the population variability. More variability in the original population will generate larger standard error, and that produces a smaller z-score. So again, mathematically, let's just say that the population standard deviation is equal to 10, and we have a sample equal to 100. So our standard error, we're solving for standard error, then would be 10 over 10, and that's equal to 1. And now let's increase the population variability, this value. Let's increase it to 100. So standard error is equal to now 100. Again, more variability, larger standard deviation of the population over the square root of 100. So our standard error would equal 100 over 10. And our standard error would equal 10. So notice that as I increased the standard deviation of the population from 10, this value, to 100, the standard error went from 1 to 10. So again, affirming this larger standard error. And why would it produce a smaller z-score? Well, whenever we calculate our standard error, if you think of this mathematically, if we divide, our z is equal to m minus mu divided by standard error. If this number increases, if you divide by a larger number, the quotient is going to decrease. Conversely, if you divide by a smaller number, the z-score is going to increase, meaning the quotient of this mathematical equation. So again, more variability in the original population lends itself to a larger standard error. Larger standard errors will produce smaller z-scores and consequently decrease our ability to reject the null, because smaller z-scores mean that they're closer to the center of 0. And that's usually the region where we would fail to reject the null hypothesis. So I've said before in previous lectures that the researcher is always hoping for large mean difference and low variability. And here we see mathematically why that is the case, because larger variability essentially is going to make it harder to detect patterns or harder to detect differences based on treatment. So again, mathematically, let me show you what this means. A z, let's say the mean difference, just for the sake of making this problem easy, mathematically, let's say it's equal to 10. And we use this standard error of 1. So 10 divided by 1 is equal to 10. And then z is equal to 10. And we use the larger standard error of 10. And we get a z-score equal to 1. So again, notice that this value of 1 was generated because we had less variability, and the z-score of 1 was a result of a standard deviation that was larger, which produced a larger standard error, and we have a smaller z-score. So again, this affirms that more variability will produce larger standard error and yield a z-score that's smaller, meaning it's closer to the center of 0, and decreases our likelihood of rejecting the null. I forgot for the first point to express that other point, that larger discrepancies between m and mu will produce larger z-scores. Larger z-scores mean that we increase the likelihood of rejecting the null. Again, the likelihood of rejecting the null is larger when we have large differences between the sample mean and the population mean. So again, I'm going to erase all of this so that we can discuss the third point that relates to the sample size that we use. And finally, we'll look at the effects of different sample sizes. So number of scores in the sample, large N will yield a smaller standard error and produce a larger z-score. And if I want to, I'll make sure I'm more consistent with the way that I notated it previously, so larger z-score. So let's just play with some numbers to see what this looks like. So our z is equal to m minus mu divided by standard error. Our standard error is equal to standard deviation of the population over square root of n. Let's consider n equal to 25, and n will increase it to 100 and see what happens. So if our standard error is equal to, and again, I'm just going to make up numbers just so we can see the mathematical relationship between these variables. Let's say it's equal to 10, the standard deviation of the population, divided by the square root of 5, and we get standard error equal to 10 divided by 5 is equal to 2. And we'll hold that value constant so that standard deviation of the population is equal to 10 over the square root of 100. And the standard error now is equal to 10 divided by 10, and we get 1. And so what does that mean? Again, we looked at the relationship of what happens when standard error changes. In other words, when we look over here at our z equation, if you divide by a larger number versus a smaller number, so again, the smaller sample size of 25 produced a larger standard error in comparison to the sample size that was larger, which equaled 100. That produced a smaller standard error. So again, here we see larger sample size will produce a smaller standard error, and we saw that. Larger sample size from 25 to 100 illustrated here produced a smaller standard error to compare to 1, and then that's going to generate a larger z-score. And again, the reason being is that when you divide by a smaller number, the z-score is going to increase. And again, this is all assuming everything else is, we're holding everything else constant. So don't lose sight of that we're just manipulating one variable to see what the effects would be on our z-score. So again, if we divide by a smaller number, the quotient, in this case the z value, will increase opposed to dividing by a larger number. So again, the sequence reads larger sample size produces smaller standard error. A smaller standard error will produce a larger z-score and increase the likelihood of rejecting the null hypothesis. Again, larger z-scores increase the likelihood of rejecting the null. So I'm going to just put a little notation here so that you can write it in your notes, because these relationships are very important and will be used and referred to in the subsequent chapters pertaining to a t-test, the family of t-tests. So here again, we say as the difference between, excuse me, m and mu increases, z increases. And then here, as standard deviation of the population increases, standard error increases, and z decreases. And then finally here, as n increases, standard error decreases, and z increases. So hopefully that notation helps you when you're referencing it in your notes, because again, it will be very important in subsequent chapters as well as in this chapter, obviously. Okay, we'll end with a learning check. Again, we just discussed the relationship between these variables, so let's take this scenario into consideration. A researcher uses a hypothesis test to evaluate the null statement, which says the treated population will equal 80. Which combination of factors is most likely to result in rejecting the null hypothesis? And the factors that are going to increase our likelihood of rejecting the null is large n values, large sample size, and small variability. And variability is denoted by standard deviation. So let's just look at these values. So we can go ahead and omit the sample sizes that are larger. So we see that 50, right, are larger than 25, so we can omit these two. And then we always want smaller variability, small standard deviation. So if we're just focusing on B and D, we see that this has smaller variability. So this scenario would generate the largest z-score, which would enable us or give us a greater likelihood of rejecting the null hypothesis. And similarly, let's decide if these statements are true or false. An effect that exists is more likely to be detected if n is large. Remember, we hope for large sample sizes and low variability, so this would be true. The next one, an effect that exists is less likely to be detected if standard deviation is large. Yes, this is true, right? We want low variability, small standard deviation. Small standard deviation is going to increase the likelihood. So this is also true. It's less likely when we have greater variability. So that is true. And that concludes this part of Chapter 8, Part 4. And next we'll move into Part 5 and continue with this topic of the hypothesis test, and in particular a z-test.